All right, let's go ahead and talk a little bit about implicit differentiation. The biggest, and this was one of my hardest things to really get through my head, but until I realized it's just a chain rule. That's really all it is. And so if we take a look at the chain rule again, it says, suppose you have some function of, let's say u, such that g of x is equal to u. Okay, that means that you have f of g of x. And if you wanted to take the derivative of that, so the derivative of f of g of x with respect to x was equal to the derivative of f of g of x times the derivative of g of x. And the biggest way that people tend to, or instructors tend to refer to this is you take the derivative of the outside thing and then multiply that by the derivative of the inside thing. Okay, so, and I've already done a few examples, but let's look at a kind of a simplistic one here. And just for a refresher course, so I have x squared plus 3x minus 2 on the inside, and I'm raising that to the third power. Okay, I want to go ahead and take the derivative of this. And so the derivative with respect to x of x squared plus 3x minus 2 raised to the third power is equal to the derivative of the outside. And the thing happening to the outside is you're raising it to a cube. And so you bring the 3 down in front. It's 3 times the thing plus 3x minus 2. Now you decrease the power by 1. This is nothing more than the power rule. And so if you really want to think about this, the inside stuff is y. And you know what, for good measure, let's go ahead and write that down. Let's go ahead and write down y is equal to x squared plus 3x minus 2. Okay? So now we've done that. Now we, according to the chain rule, we have to take the derivative of the inside thing and multiply that. And so the derivative of x squared plus 3x minus 2 is equal to 2x plus 3. Okay, all of a sudden, well, wait a minute. If we take the derivative of y, all right, now we've got 2x plus 3. So that's really just y prime. So if we wanted to go about rewriting this, we could say, oh, okay, well, the derivative with respect to x of y to the third is equal to 3 times y to the second times the derivative of y, the derivative of what's inside. Now, nowhere in here did we explicitly state that y was in fact a function of x. We just assumed it could be. And so we have we have some indication that perhaps y is a function of x. Now, if it turns out to be not, then this kind of just goes away and life is good. Or we might have to do another chain rule or that sort of thing. But the idea of the implicit, when somebody implies something, they're not really stating that it happened. They're stating that the conditions were there to let us believe that it was. Okay, the implications of it were. And so that's really what I view this as, implicit differentiation. We're not telling you that y is a function of x. We're just going to go ahead and kind of assume it is. And we'll see in later problems that y doesn't have to be a function of x at all. In fact, x could be a function of something else. And that's okay. All right, so since we're implying that, we still have to take that derivative. The chain rule says take the derivative of what's inside. And so we still had to do that. That's implicit differentiation. So let's take a rather simplified version of it. Okay, so here's another example. We're going to go ahead and take the differential of x, y is equal to 3. Okay, so we're going to go ahead and take the derivative with respect to x of xy. Now, this is being multiplied, and so the derivative of something being multiplied, we have to enforce the product rule, which says it's the derivative of the first, and the derivative of x with respect to x is just 1. times the second plus the derivative of the second. Now here's the tricky part. The derivative of y with respect to x is simply that. It is the derivative of y with respect to x. That's all it is. Okay? Times the first is equal to, and now I can kind of rewrite this if I wanted to. I'm going to let that be though. I said equals to, but when we didn't know, we had to take the derivative of both sides. Okay, the derivative of y, the derivative of x times y is y plus x dy dx. And so if I take the derivative of both sides here, like I told you I would, the derivative with respect to x of xy equals 3 is y plus x dy dx equals 0. Okay? Now, if we wanted to solve for, let's say, oh, well, let's find the derivative. All right, well, that's the rate at which y changes, kind of right here. And so we have to solve for that. So we subtract y from both sides and divide by x to get dy dx is equal to negative y over x. Now we have a problem here because now our derivative actually depends on the value of the original function. And so if we go back and kind of solve for it here, so we say, okay, well, if y is equal to 3, that means y is equal to 3 over x. We can take that value and shove it right back into the derivative. Okay, so let's go ahead and bring that down here, where dy dx is equal to, and instead of y, we're going to put 3 over x. So we're going to put negative 3 over x divided by x, which is going to give us negative 3 over x squared. All right, so now we have the derivative of y with respect to x in terms of nothing but x. So dy dx is equal to negative 3 over x squared, or dy dx is equal to negative y over x. It just depends on what you might have in the end result. They might say, oh, we'll find it at a point. Well, great. Now that you found it at a point, you actually know both x and y, so you don't really need to go back and solve for y. If they say, well, what is the derivative when x is bleh? Well, now you got to go back and you have to solve for x or for y and then substitute that in so that you get a derivative that's based solely on the x values. Implicit differentiation, it's not that bad.